this lesson, we're going to look at radical inequalities. We're going to graph them like we did just the radicals, but then we're going to include the information that the inequality adds to the graph. Now, first of all, the basics for radicals with inequalities is just the same as regular inequalities. That if you have a greater than or if you have a less than, you're going to have a dotted graph. If you have a greater than or equal to or a less than or equal to, it's going to be a solid graph. And then you're going to test a point to see whether it's shaded above or below the graph. Now there's one extra addition here that we're going to add on, and I want to make sure that we emphasize it in a couple places, is when the even index, when we have an even index, it adds a boundary. So we'll talk about that when we do the even ones. And that's because the domain is restricted with the even index problems, and it's not with the odd index problems. So let's take a look at this first one. This is the cube root. We've got a less than or equal to, so this means we're going to have a solid graph, not dotted. This here, when we have x minus 3 plus, and then the plus 4 outside, remember what that means is out at 3 and then up at 4, we're going to have the turning point. This graph is going to, when we have a graph that comes in like this, there's a point here where we'll call that the turning point. We want to find that first. Well, that's the point here, 3, 4, because of that. The opposite of inside, the same as that one. Let's take a look at what the graph looks like. So if we were to take a look at our graph of cube root of x minus 3 plus 4, the cube root, by the way, just as a reminder, if you look at the math menu, you not only have the cube root, but you have an x root here. So you could do other roots higher than square roots and cube roots by using this math menu. So we'll take a look now at the graph here. Notice here's our graph where it's coming in, and then it goes up, and then it turns right at this point 3, 4. Well, if we want a couple other points here, let's go ahead and look at our table. And our table tells us that we're going to have, for instance, 2, 3, 4, 5. Let's get one a little bit higher here, maybe -5, 2. So I'll go out here to -5, 2. And then we had then we had down here, closer to the turning point, we had 3, 4, and we also had 2, 3. So our graph basically looks like this. It's solid, remember, and then it's going to go like that. All right, so solid graph. Now we got to decide, do we graph above it or below it? Now above it or below it, we should test a point. 0, 0 is a great point to test here. Put in 0, 0 here. Is 0 less than or equal to the cube root of 0 minus 3 is -3. That's going to be a negative plus 4. Okay, so is that a true statement? And if you notice that, it's going to be. This is a really tiny number, tiny negative. If you add to 4, if you put that in your calculator, you'll get a true statement. So it's going to be shading below here on this graph. Let's try this one. Notice that this is a fifth root. Our turning point is going to be at -1, -2. So right down here is our turning point. We're going to go ahead and look at our couple points on our graph here. So if we go to y equals here, I'll turn this graph off. I'll turn this graph on, and then take a look at the graph. Notice that this turning point is right there at -1, -2. And if we look at the table, we get some other points, like it goes through 0, -1, goes through -2, -3. So -2, -3, and 0, -1. And if you need to, you could get a table with some more values. That our point here is not to do as much about the table, but I want to point out that you get the exact points from the table. Our point is to go ahead now and put a dotted graph. This means that we're going to have a dotted graph, and we're going to decide then, once we do the dotted graph here, Is it gonna be shaded above it or below it? Well, what do your instincts say with the greater than? It tells us probably above it. So let's go ahead now and test a point. We're gonna test 0, 0. If you put in 0, 0 into this inequality, you get 0 is greater than the fifth root of 1 minus 2. That's gonna be 1 minus 2 is -1. That's a true statement. So you're gonna shade above because 0, 0 is above that one. So when you do the odd index, it's actually not so hard to do because you do dotted or solid, and then the inequality is pretty easy to figure out which side we go on. Now the even index, we need to add what's called a vertical boundary. And this is going to be solid with an open or closed dot. Now let's talk about what that means. If we do a problem like this, notice that, and I'm going to use this one and sketch it out for us. If we do this one, this means it's going to be a dotted graph and an open dot. Okay, so let's go ahead and put in, do this graph. This would say that we're going to be at 2, 5. So up here, this is our starting point. I want to put that starting point as an open dot. Now if I look at my graph, we go ahead here and get rid of this second one here, stop that graph, and do this graph. So if I look at this graph, notice that it has a starting point there, and I'm going to do a dotted graph here. Again, use your table on it to come up with the actual values if you need to get a more precise graph. But then, is it going to be above or below? This tells me it's going to be above. If you put in 0, and you graph this one, notice you put in 0, 0, it's going to be a false statement, but 0, 0 isn't even above or below the graph. So notice 0, 0 is not a good point to graph because it's over on this side of the graph. I would have to test a point either up here or down here. Like if I tested the point 4 for x, this would be the point 4, 0. If I test that point, is 0 greater than the square root of 4 minus 2 plus 5? And if you do that, this is the square root of 2 plus 5. Is 0 greater than that? No, because this is a positive number. It's not. So I'm going to shade on the other side of the graph here. So make sure you're not testing 0, 0. It's got to be above or below this actual graph as it's been translated. Now, here comes the vertical boundary. There's a stopping point here, and we have to draw a solid vertical boundary here because it's solid, because if you put in any point in this on this boundary, like if you were to put in the point 2 comma this point right here, let's say it's 2 comma 7, if you were to put that into the inequality, it would be a true statement. So there's always a solid boundary on the edge of the domain, and then you shade on the other side, but there's an open or closed dot at the end of it. You got to make sure you include that open dot, whereas this one will have a closed dot. So always a solid boundary with an open or closed dot. Let's take a look at this one. We're going to go ahead and this is going to be a solid graph. We're going to do fourth root of x plus 5, so we're going to start at -5, so out here at -5, up at 2, so I'm going to start right there with a solid dot. So this is not only a solid graph, but it's going to have a solid dot as well. Both of them, so either open graph, an open dot, or solid graph, solid dot. Now this one, if you look at the graph, again, you could put that into your calculator, and let's not do that one, let's do this one instead. If you look at this graph, notice it comes right over here. It doesn't tell you it's dotted or solid, notice, because it's just graphing the boundary. And then if I do that graph here, and I go over to this end here with a solid graph, This tells me it's gonna be below. If you test a point in this arena, now 0, 0 would be an okay one to graph or to test because it's in of either above or below the graph. Is 0 less than or equal to the 4th root of 5 plus 2? And the answer is yes. So you shade on that side. And then you put a solid vertical boundary on this side of it because that line ends the domain there. Every point on this boundary, if you put in -5 comma 0, it would work. 0 is less than 0 plus 2. And so the boundary is always solid. It's just the dot at the end matches what the inequality is, and the graph itself matches whether it's dotted or solid. So in summary, with the odd ones, you just draw the graph, dotted or solid, shade above or below by testing a point. But with the even ones, you not only have to draw the graph dotted or solid, but you have to put an open dot if it's not an or equal to, put a closed dot if it is an or equal to, and then draw a vertical boundary on that side to give a boundary for the domain. It's always a solid boundary though for that inequality.